Hello everyone, welcome to week 6 data system design live session. I am Om and today we will solve some questions that will help you in your assignments. So in this week we will be covering the arithmetic circuits, mainly adders, and a bit overview of multipliers using adders. So let us start with the first question. Which of the following represents logic values of carry generation and carry propagation after the addition of A1 and A1 and B1 bits in an adder if A3 A2 A1 A0 is 0 0 1 1 0 and B3 B2 B1 0 are 1 0 1 1 are inputs to the adder. So if you have seen the video for look ahead carry adder, you know that the generation is AI into BI and propagation is AI plus BI, right? So if we take A1 and B1 bits, A1 B1, this is A1 plus B1. A1 is 1, B1 is also 1, that is P1 is 1, this is A1 OR, that is also 1. So please note this is not addition, this is OR and this is AND. So the answer is logic 1 and logic 1. I hope this is clear to all.
So we should do only for the first bit.
What?
This AIBI only for the first bit.
What do you mean first bit? Sorry.
Like only A1 and B1, not
So
A0, B0.
it was given question to do for A1 and B1. That's why I did for A1 and B1.
Okay, sir.
Yeah. Okay. So moving on. So select the correct expression for sum and carry of full adder circuit. So uh, I think you all can do this. This is an easy question. So what you can do is maybe make a truth table first. Let's say A, B, C and sum and C out. 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 0 1 1 1 0 1 1 1. So when sum is 1 when either one of these is 1 or all three of these is 1. So 1 here, it will be 0 here, 1 0 0 1. And when is carry 1, when any two or more of them is 1. So carries will be 1 here, 1 here, 1 here and 1 here. Rest all are 0. Okay, so this is sum and carry. Now what next you can do maybe is you can uh, make a truth table. Oh sorry, make a k map. So if you make a k map for let's say so you have one at uh, 1 2 4 and 7, right? So none of these make a pair, and this is the characteristics of XOR, or you can write it as, if you have to write it, what you can write it as is A bar B bar C plus A bar B C bar plus A B bar C bar plus A B C. This is XOR A XOR B XOR C. For carry, what you can do is this is carry. So this is A bar carry is AB plus BC plus AC, right? Now what you can do here is AB plus C A plus B. Okay, so if you see, none of these have, okay, we have something similar to let's say this one, but still it is XOR and we have a plus here. So let us examine this. Let us see. Let's do AND and XOR, sorry, OR and XOR. Okay, so this is the difference between OR and XOR. So now let's see. So in any case, let us say if we take this whole expression, if I take, let's take, first case is this, second case is AB plus C A XOR B. So what is the answer for this one, this case? Because only in this case the OR and XOR are different. So A dot B will be 1 plus C, let's say C is whatever, A plus B is 1, in the second 1 plus C times 0 in case of XOR. But the thing is, your 1 plus something is always 1 in Boolean, right? So it does not matter. So we can take both, either or XOR gate. Why do we tend to take XOR gate? Because in a full adder we have AB is A XOR B, C, A XOR B XOR C. Then for carry, we can directly take the take this as one of the input. If we have this A XOR B, then AND it with C, then OR it with AB. This is carry. So just because this is available already, we tend to use XOR instead of OR. Therefore, your sum is this, your carry is this. That is option B. Is there any doubt?
No, sir.
Okay. So, just a moment. Okay. So, the next is, what is the minimum delay to produce sum and carry in a single bit full adder circuit given by the expression in question 2? Delay and number of inputs for individual gates is given as this. So, for this, let us make the circuit again. We have 2 input XOR, 2 input OR, and 2 input AND gates only. So, if we have to make AB, A XOR B, C XOR B XOR C, this is the sum. Now for carry, you need, what was carry? Carry was, let's say C out was AB plus A XOR B into C. So we need this, and an AND gate with C is going into an OR gate, AND gate A and B is going into the OR gate, right? This is carry. Now if you look at the propagation delays, this is a propagation delay of 2, this is of 2, this is of 1, 1, and this is of also 1. So the propagation delay in sum is 2 plus 2. So TDS is 2 plus 2, that is 4 units. Now in carry, if you see the largest part, 2, 1 and 1. This is also 4. 2 plus 2, 1 plus 1, that is 4U. So your answer should be uh, 4 and 4, but none of these options have 4 and 4. So these options are incorrect. Your answer should be TDS equals to 4U, TDC equals to 4U. Is this clear?
Sir, for A and B also it requires 1 nanosecond.
Sorry, what?
Should we add it as 4 plus 1
Where?
for AB, A into B?
Yeah, okay. So this is the what you can say is the worst case delay, right? So by the time A and B are available to you, A, B, and C are available to you from the starting. By the time this is happening or this is happening in parallel in a separate gate, right? So
Yes, sir.
it does not depend on anything coming from behind. This depends on the output of this. That's why we added 2 plus 1 here, right? But this does not depend on any previous gate.
Okay, okay.
Okay, so this is a theoretical question. Maybe you guys can tell me the answer better. Okay, so anybody has any guess for this one?
C.
Yes. So if you remember, for carry, just for carry, we have, let's say, if you have 5 bits, we will have G1, G2, G3, G4, G5, 5 generation and 5 propagation. So it gets seriously complex as the number of operands increases. Okay. For a particular design of multiplication unit,
7.
yes. So let's say this is n and this is m. Your answer is always n plus m. And how many adders do you need here? You need m adders, each of size n plus m bits. Okay, so next we have is given the ripple carry adder circuit, which is used to add 8 bits, A7 to A0 and B7 to B0. If carry generation is 15 nanoseconds and some generation is uh, delay is 14 nanoseconds, what is the worst case delay of this adder circuit? Consider carry propagation delay to be 0. So let's just try this. So we will need 8 full adders for sure. It says C0, C1, C2, C3, C4, C5, C6, C7, and it will produce the last output C8. Right? These are the carries, successive carries. And This can be S0, S1 till S7, right? A0, B0 till A7, B7. Now, if you see the propagation delay for the carry, let's say C0 is available from the beginning, if we assume, then uh, for the final carry generation, if 15 nanoseconds is for generation of C1, then 15 for C2, then 15 for C3. So it is for till C8. To generate C8, we need 15 into 8, right? 15 is given is as the generation delay for carry. So this is 120 nanoseconds. And for sum, what it will be? So till here, till C7, we need 15 into 7. Once we have C7, we just need this one sum generation delay, right? Which is plus sum generation is 14 nanoseconds plus 14, which is 105 plus 14, which is 119 nanoseconds. So the worst case delay is 120 nanoseconds. Is this clear?
Yes, sir.
Okay. So this is a similar question. So you can attempt it maybe. 'So what will be answer for this one?
121.
Right. So for carry will be same, 15 into 8, that is 120. For sum, it will become 15 into 7 plus the only thing different is 16. It's 121. So now the answer is the the maximum proportion delay is 121 nanoseconds. An adder is designed that adds 10 operands of single bits. Which of the following adder architecture would require minimum number of gates?
Is it carry save adders well?
Yes. So carry save adder saves the uh, maximum amount of area as well as delay. So that means it uses least number of uh, adder units. So the example is given in the video. You can realize it like if you have like A0, let's say A10, A sorry A9, A8, A7, A6, A5, A4, A3, A2, A1, A0. Let us take this is one full header, this is another full header, this is another full header. Then you keep on passing this. So this is again we write 2 to the power 0 is this one. Give 2, 2 to the power 0 and 2 to the power 1.
चलना है क्या? बस से नहीं कैसे जाएंगे हम? ठीक है फिर मैं अभी कैब करती हूँ फिर चलते हैं.
This is your S0, this is
हाँ.
S1, S2, S3. This is the half header. Rest all are full headers. You need 1, 2, 3, 4, 5, 6, 7 full header, 1 half header. So this is more clearly explained in the video. I just draw on it roughly. Anyways, it is carry save order. Which of the following represents a 7-bit address line add in Verilog?
3.
Yes. So 620 means 0, 1, 2, 3, 4, 5, 6. That is total 7 lines. And you define the wire, then write the uh, name, that is this, sorry, the one above. For a particular design of multiplication unit with 6-bit multiplicand and 3-bit multiplier, what is the worst case number of adders required for the design? What would be the size of those adders? So this part we had solved in one of the previous questions, right? This is N, this is M. What is this?
7. 6 plus 3.
Yes, this
9.
is N plus M. And the number of adders is M. So you need 3 adders with, that is 9 bits size. So the answer is this option. Okay, so this is an interesting one. How many 4-bit adders are required to design 16-bit carry select adder? Assume equal groups of sizes 4-bit adder. Inputs are A15 to A0 and B15 to B0 and C0. Sorry, I had lost connection. So what we have is we have to make 16-bit carry select adder using 4-bit adders of equal groups. So what we have is, let's say we have 4-bit adders. Like a general, we can say intuition is 16 by 4 is 4. So let us first try 4. So this can add A50. Let's start from here. A0 to, I can say E3 to A0 and B3 to B0. This can add A7 to A3, B7 to 3, 11 to 11, 15 to 11. So let's say these are 4-bit adders. Right. Now one thing we know about carry select adders that is special is the redundant units that they have. Right. It will have exactly same 4-bit adders. One of them will have C in 0, one of them will have 1. 0, 1, 0, 1 and 0 and 1. Next they will have mux, which will decide which one is the output, right? right? So on and all, due to the redundancy, it requires 8 adders, 8 4-bit adders. Is this clear?
Yes, sir.
Okay. So this question was also explained well in the last video. What is the size of array multiplier that is required to perform multiplication of 6 bits given number as M5, M4, M3, M2, M1, M0, P5, P4, P3, P2, P1, P0. So if you remember, the area was of the order of n square. So you can simply choose 6 cross 6 as the array multiplier. Right? If you remember, it was explained in the video with the 5 cross 5 example, something like this. Which you like, okay, which you like count. Actually it is not 5 cross 5, it is actually 4 cross 5, but in general we take of the order of n square, but actually it is 4 cross 5. So if you answer like 5 cross 6, that is also not incorrect, but for a very large system we tend to ignore this computation and we go with uh, of the order of n square. Let's say if it was 100 cross 100, if there were 100 bits, so saying 100 cross, saying 99 cross 100 and 100 cross 100 would not make any difference. So remember, for multiplication is always of the order of n square. Are you able to recall this from the video? Is it clear? Okay, so I guess uh, Nishant,
Yes, sir.
do you get it?
Yes, sir. Fine.
Okay. So next one is also similar. What is the area requirement? If you go by order of n square, you will get answer as 36 into 1 FA. But if you go by like 6 5 cross 6, you get 30 into 1 FA. So this is quite a hazy question, but NPTEL tends to go with the answer of 36. So if you get similar question in an assignment, go with the order of n square. Again, this is not incorrect, this is also correct.
आगे क्या अब
Okay. In a design of 5-bit single level carry look ahead adder, what is the maximum number of fan-in of an OR gate? So what you can do is let us understand it with the diagram itself. So if I search for look ahead carry adder, right? So if you see, if we go for a 4-stage, okay, let me take this screenshot. Right, so if you see here, if we have 4-stage here, right? Now if you see the number of operands here in the and in the OR gate, so 1 2 3 and 3 4 and 5 itself, right? So if we see the gate, so this is the diagram. So for 4-stage you require maximum of this top OR gate is giving C4 has 4 inputs, so it has a fan in of 4, the maximum fan in, that is depending on the number of stages. So for 4-stage you will have a fan in of 4. So in this question, for a 5-bit single level carry look ahead adder, the maximum fan-in of an OR gate will be 5. So which is highly impractical for an OR gate if you see, and it is very difficult to make a OR gate with 5 inputs. So we tend to see why the look ahead carry adder is a very complex circuit, which we had answered in one of the questions, theoretical questions. Okay, so just keep in mind, if you have 5 bits, n bits, n fan-in. It's not very important, just theoretical. Okay. So in this question, we have a carry select adder. In a carry select adder, when unequal groups are formed to perform n-bit addition, then what is the largest size of the adder required? So if you remember the video of carry select adder, so the answer to this question is root n. So again, like, I understand it is little difficult to get uh, this understanding without uh, with just the theoretical knowledge, but yeah, these are just some numbers that you should remember.
would have been
So if you remember, for carry select adder of unequal groups, you need largest adder is of root n size and delay of adder is 2 root n plus 2. So this is explained in the fourth video of this week. Okay, so I do not have any more questions. So if you have any doubts, you guys may ask.
So for the exam, what type of questions we can expect, sir?
So mostly what I expect is like uh, Verilog is very important. So you should practice Verilog very well. So just like these simple questions are just syntax, right?
Yes, sir.
This does not have any, if you see that Verilog, yeah, these two like just to confuse you with the syntax. The logic was till only till this 6
Yes,
to
sir.
0. So you should practice Verilog very well. First of all, that is the I think goal of the course that you learn Verilog well. Second thing is again everything is like basic logic, right? There's not uh, much of very hard anything. There is nothing very hard. Everything is very logical. So if you know the basics, like you know how to read a root table, how to make k-maps, how to simplify things, and then just the basics of what is an adder, what is a multiplier, that is like
Yes, sir.
that kind of theoretical knowledge is enough. And I think the assignments as well as the questions I give you are sufficient, and you may even see mostly in exam the questions repeat from assignments also. So I
Okay,
suggest that
sir.
practice your assignments, or like do not make the mistakes that you made in assignment again in the exam. That's
Yes,
the
sir.
only thing. So for two things you should focus. First is Verilog. Second thing is the basics of the concept whatever are being taught. So you should like even to solve assignments, like very small, very minor details of the videos are being picked into these assignments. So you should
Yes, sir.
review those videos very well, right? If there is any theoretical knowledge like that n plus m thing or root n thing. So this is all like you can just write down in a piece of paper and prepare some very short notes, and just before exam you can just revise them and have that in mind.
Okay, sir. So can we get previous year question papers? I'm not able to get them.
I don't think that is publicly available. Uh, so that would be difficult, but I think what happens is that one of the uh, one of the guys from NPTEL who is like related to this course, or one of the other course tiers, what they do is they just before an exam they take a session, a live session on YouTube, I think, and they like tell you the kind of questions there, what you can expect, or how some tips or tricks for the just for the exam. Just I think that will happen after the 12th week. So look out
Okay,
for
sir.
that. So uh, that will also help you a lot.
Okay, sir.
Yeah.
Thank you, sir.
Okay. So I apologize, like I had to prepone this session, but I think there was some mistake made in the announcement. So they announced it. I just saw it. They announced it from 6 to 7.
Yes, sir.
Was
6-2.
But I had told them to I'll take the lesson from 7 onwards. So okay. Anyways, I am sorry, but yeah, I'll upload the recording as well as the lecture note for today.
Okay, sir.
Yeah. Okay. Thank you, both of you.
Thank
Yeah.
you, sir.
See you next week.